In the last lecture, we saw various mechanisms of drug absorption: passive diffusion, facilitated passive diffusion, active transport, pinocytosis, etc. Coming to the passive diffusion, drugs move from the region of high concentrations to the region of low concentrations. So drugs should cross the barrier. What is the barrier? Is the cell membrane. We knew that diffusion rate is directly proportional to the concentration gradient. That is, drugs move from the region of high concentrations to the region of low concentration. But it is also depend on the other factors such as the drug molecule's lipid solubility and the area of absorptive surface and the degree of ionization and the size of the molecule. Coming to the lipid solubility, we know the cell membrane is a biphospholipid layer. So it is lipid loving. So lipophilic drugs can easily pass through this membrane, cell membrane. And coming to the size of the molecule, small molecules can easily pass through the cell membrane rather than the larger molecules. And when we talk about the area of the absorptive surface, more is the area, then the more is the absorption, and it's vice versa. And we told it also depends on the degree of ionization. So to talk about degree of ionization, we need to know the relationship between pH where the drug is present, pKa of the drug molecule, and its extent of ionization. This is the pH at various places of GIT. So as we move down through the GIT, pH increases. So you can see pH is 8, almost 8 in the large intestine, where the pH is 2. It's nearly 2 to 4 in the stomach. So how this pH affects the absorption? So let's see the relationship between pH of the medium, pKa of the drug, and the degree of ionization. Majority of the pharmaceutical drugs are either weak acids or weak bases. So before seeing how these weak acids or weak bases are absorbed at various pH as it travels through the GIT, first let's dig into some basics. So strong acid is the one which it ionizes completely. So completely it gives the ions when it's put in the aqueous medium. Aqueous medium may be anything which is aqueous like water. So when it's put in water, it ionizes completely. Consider hydrochloric acid. When it's put in a beaker of water, it completely ionizes to H plus and Cl minus ions. So it's adding a proton to this water. So anything which adds protons is called as acid. Strong base is also the one which ionizes completely when it's put in the aqueous medium, but consider sodium hydroxide, which is a strong base. When it's put in the water, it ionizes completely to Na plus and OH minus ions. But here it takes up the proton from the water. It takes up the proton from this H2O and it becomes water. So it takes up the proton from the water. So anything that takes up the proton is considered as a base. So anything which gives proton to the water is considered as a strong acid or acid. Anything which ionizes completely is a strong acid or a base, but which does not ionize completely. So the ions are not completely formed in the case of weak acid or weak base. So the equation, it lies in the equilibrium between the unionized form. Here this is unionized form and this is ionized form. So here ions are formed is the ionized form, ions it is the unionized form. So it exists in the equilibrium between the ionized form and unionized form. So this is considered as the weak acid. Unionized form of the drug is lipid loving or it is lipophilic, whereas the ionized form of the drug is water loving or it's hydrophilic. Since we knew that the cell membrane is lipoid or lipid membrane, so these lipophilic or unionized form of the drugs can easily pass through the cell membrane. So we saw the pH at different places as we travel down through the GIT, and we saw what is a weak acid. So let's see the term pKa. So what is pKa? What is its relation between the pH and the degree of ionization? So pKa is referred as pH. So at any pH where the ionized form and non-ionized form exists in equal ratio. So 50% it exists in ionized, so 50% it exists in the non-ionized form. So this is referred as pKa. So let's consider aspirin. Its chemical name is acetyl salicylic acid. So when it enters GIT, it ionizes to carboxylate anion and H plus is a proton. So this is the chemical equation. So the pKa of aspirin is 3. Generally they say pKa of the drug, but it's actually the pKa of the functional group. So the functional group present in the drug molecule tells the pKa. So how this drug with the pKa value of 3 behaves at pH 2? Maybe pH 2 nearly the pH present in the stomach. So the degree of ionization can be calculated if we know the pKa of the drug and the pH of the medium it's present. So this is traditionally calculated using Henderson-Hasselbalch equation. So the Hasselbalch-Henderson equation is like this: percentage ionization equals to 100 by 1 plus 10 to the power of x into pH minus pKa. So in this equation we know the pH of the medium maybe is 2 and the pKa of the drug is 3. So the left side of the equation remains the same. So x is minus 1 for acids, whereas x is equal to plus 1 for bases. We knew acetyl salicylic acid or aspirin is a weak acid, so here x is minus 1. So minus 1 into 2 minus 3. So 2 minus 3 is minus 1. So minus 1 into minus 1 becomes 1. So 10 to the power of 1. So 1 plus 10 is 11. So 100 by 11, which gives 9. So 9% of the drug exists in the ionized form in the pH of 2, whereas 91%, 100 minus 9 gives 91. 91% exists in the unionized form in the pH of 2. So majority of the drug exists in the unionized form at the pH of 2. So 91% of the drug exists in the unionized form. So this amount of drug can easily pass through the biphospholipid membrane layer at the pH of 2. So in the same way, we can calculate the degree of ionization for various drugs if we know the pKa of the functional group or the pKa of the drug and the pH where the drug is present. So this is the traditional equation to calculate the percentage of ionization. But there is a shortcut to find the percentage unionized and the percentage ionized based on the difference between the pKa and the pH. So let's assume pKa of the drug is 5. So at various pH, how the drug behaves and what is the percentage of unionized and ionized, we can know by simply subtracting the pKa and the pH. So if the difference is 4, it indicates 4 nines. So 99.9% is unionized. So 100 minus 99.99 gives 0.01. So that is the percentage ionized. So at the pH 2, so 5 minus 2, the difference is 3. So 3 nines it, and the difference is 99.9. So 99.9 exists in the unionized form, and the difference of 100 minus 99.9 gives 0.1, which is percentage ionized. So this is the shortcut to find the percentage unionized and the percentage ionized. This almost matches with the Henderson-Hasselbalch equation. So this almost matches with the Hasselbalch equation. So here you can see the difference is 0 and 50% exists in the unionized form, 50% in the ionized form. So this is the pKa. So pKa is the pH at where 50% of the drug exists in the unionized form and 50% of the drug exists in the ionized form.